So let's try to develop new turbulence model, and for that what we do, we try to adapt the k omega SST model, okay, and we try to modify the k omega SST model and incorporate some scale adaptive type of the scenario inside the k omega SST model, and then we try to develop another class of the k omega SST model where we have SSH based k omega SST model. So let's try to understand few concept how one can develop the new turbulence model. So in the previous case we adapted the template, so we ultimately constructed the template, and now we know how to fetch the template out of the actual source code. So let's do it the same task again. So for that, let's go to our code area, and we try to stick to fetch the template from extended version as compared to the release version, because whatever the version I have installed is 3.0x, and after compilation when we go for running, it showing us the error, and I'm not able to rectify that error, okay. But if we follow the extended version 4, we're not going to get any error, okay. But it's not necessary that you stick to extended version 4 only. Other than 3.0x, whatever the version is installed on your PC or desktop or laptop, it's going to work the same methodology, okay. So how to proceed? Let's first fetch the template again. So let's go to the area where it is exactly installed. So form extended 4.0 src turbulence models incompressible runs, and we want to look at the k omega SST model. So let's copy this from this area towards our area, okay. And first let's rename this in, so I say my k omega SST, okay, and at the back I say FE4, so extended version 4 we're going to use for this. Fine. So now immediately also change the name of our .c file and .h file, rename it, let's say .c file, same way .h file as well, okay. So we done with this. Now what required? We required the make folder. So let's look at from where we copied nearby. We have any make folder? Yes. So let's add up that make folder from this area, copy here, go to the make folder, open both the files, okay. So both the file is open, and now what required? We don't require anything this except k omega model, okay. So let's retain this k omega, but I want my k omega as a name of file, and what else? I don't require anything of it, okay. Let's change this to the user libbin, okay, and this library name, let me follow exactly the same name what we use in the previous case. So go to the file, okay, we say my k omega turbulence model. In the similar line I will write here, let's say my k omega SST model, okay. So we are consistent with our own developed library name. So with this we are set with the file and this, but later on we have to modify certain thing inside the options. So let it open that file. Now go to this both the files, and we have to change the name from k omega model, okay, k omega SST to my k omega SST model. So we try to replace inside H file and C file k omega SST word with my k omega SST word, okay. So replace everywhere, okay. So here we are set everywhere. Similarly inside the .c file as well, so inside of it, so everywhere we replaced the name, okay. So we are set with the name, and now we are ready for compilation. So let's go to the area FE40, first type wclean all, okay, then wmake and libso, because we want to develop the dynamically linkable library. Okay, so it's going to give us this error, runs model.h file is missing. Okay, so runs model.h file is missing. So now let's search this file inside the our release version. So when I say inside the release version, go to the application area of extend application, let's say utility, try to look at inside the utility anywhere we are have that runs.h file, that is what we are using. So if we figure it out, this runs.h file in any of the utility, and try to adapt that option file from that utility, and be able to manage our requirements. So if you look at here in the post processing area, post processing turbulence area, here we are using this runs.h file. Okay, so let me go to there, post processing turbulent. Okay, r, look at its option file. Okay, if you look at its option, what it has this 2 line. So let's copy, add up this 2 line from this area towards our option area. So this line is there, so no worry. Then what else here, we have a runs model, this file is included. So let's check that this file is included as well. With this, now try to compile it and check. So we are set with that, but it's showing another error. Okay, this one, compatibility wall function error. So we have to search where exactly this particular file is located. Okay, so it's normally, it's, if you try to look at this file where exactly it is available. Okay, so for that, again go to the area. Okay, this time we have to search inside the, if you try to search here, it will not going to give us any idea. Inside the utility, inside the application also, you will not going to get this file anywhere. Okay, because okay, that is available solver combustions k epsilon, and it is included there itself. Okay, so if we want, we try to check this location as well and have an idea. Either it is so let's say in this area, then let's say make folder not available. So any place here, no make folder. Do we have make folder? Yes, here we have make folder. Then just check the option file of that does. Okay, so look, we included few of the lines, but which line we included so that we able to rectify that error, we don't know, but that file is used inside of it. So either of this line, some of the line is useful. Okay, so if you see, all this is not belong to the turbulence modeling. So if I check the lines that is belong to turbulence modeling, then I come across this 2 line only from this area. Okay, so out of that, this line is available, only one, sorry, only this line is additional line. Okay, so if I include this line inside our area, maybe we are set with our requirement. Okay, so I say runs and include, and then if you try, okay, so check it. So we are set. Why we able to rectify this dependency error? Okay, okay, some additional error we are seeing, that is auto create omega. So somewhere it is saying that was not declared in the scope, some auto create omega or auto create. Yes. So let's try to check that, but that error is gone, what we were facing previously. Okay, so let me look at that particular area where it is showing the error. It says that auto create k was not declared in the scope. Okay, so from the k omega line 255, so let's go to k omega dot c file line 255. 255. So this auto create k, okay, and auto create k, okay, what it's saying is that was not declared in the scope. Okay, so that means this particular line required some additional libraries that is missing as far as this thing is concerned. So how to rectify it? So auto create k, then auto create omega. Okay, so let's see, anywhere we have that class of entry in the .h file. Okay, so auto create k, auto create omega. Let me check this, copy, Control F, find. So we don't have that entry, correct? So what it exactly doing, it try to create the k omega nut as a auto create way. Okay, so let figure it out how to fix this. Auto create omega, auto create this entry. Okay, let me see any additional file. They use k omega sst only, and inside the h file did we use the runs and wall this. Okay, so let's go to the src folder again and try to figure it out, different turbulence model, and have an idea how it is coded about this particular auto create option. So runs, okay, let's say k epsilon model and c file if you see. Okay, so here we have auto create k, correct? Okay, and we able to compile that file in our case as well. So that means something is missing till in this area. So go to the FE options. Okay, check anything that we didn't included. So we included all these entries or not. Let me check in our option area. Okay, so we included this file, correct? Turbulence. Okay, so this file is missing. Okay, so with the help of that, maybe we able to set that error, turbulence auto create. Maybe it is the part of that concept. So with the help of that, maybe we able to resolve it. Okay, till we have error. So let's see any additional things that is missing. Include finite volume, lib lu, decompose. So let's copy entire of this, because here we are sure that with that we didn't got any error. So turbulence model, transport, incompressible single transport, I don't think so it is needed there. Turbulence model, okay, runs model, then LES not required. Okay, finite volume, LES, no idea why, but let me add up the entire of this option file and check then if. Okay, so boldest says that fatal error, wall disk file is missing. Okay, so wall disk file is missing. That means let's see, come back again. So if we look at here, tool, we have finite volume, FV, incompressible, okay, runs model, turbulence model, runs model is included here. Fine. Okay, from this area if we see, what else we have, we additionally we have this one line. So let me add that line here. Then mesh file is included here, it was not included, that's why that error we got. Okay, in this area if we include this line here, okay, whatever the error we got here, we not able, we get rid of that error. Which error I am talking about? This error. Okay, this verdict. Okay, '41 line number. Okay, anyway, so we are set. So I think that auto creation, whatever the error we are getting, okay, so here we included this, everything was set. Okay, I don't think so it is belong to this, maybe this LES, whatever this entry we have. Okay, so let me delete this entry and have an idea exactly. Okay, so if we go with that, so sometimes it is very difficult to resolve this dependency. Okay, so for that we supposed to know in what different functions the similar type of the things is called. Okay, so that is set. Okay, then I added this entry. Okay, so LDU, let me check that till it is showing option line number option 8 1 is here, correct. So we are set even with that also. So this is one additional line we added. Okay, let's see with that also auto creation error we are getting or not. So we are set with that also. So transport model, I think whatever we have was correct. Okay, so no worry, fine. But so this is fine, this is fine, all are fine. So if we apply it again, it's perfectly all right. Let me clean it, check. So what it's saying in the options line number, finite volume, backslash and new line separate by the space. Okay, backslash and new line is separate by the space, so that is needed anyway. So fine, so we are set with this K omega SST model. Now okay, I didn't save, maybe, yeah, I didn't save, that's why it's, let me clean it. Warning, backslash and new lines separated by the space at the finite volume include here, but finite volume include, this is, I seen it's perfectly all right. I'm not able to identify why it's showing me that error. Okay, anyway, it's compiled correctly, so no worry. Okay, so if you, this is the FE, this options. Okay, so I'm copying this again into our area. Okay, and I am including this one line, okay, over here. Okay, and then I am deleting this all entries. Let's see till we are getting the same warning sign. so it's now showing at a transport single option 7. Okay, this is multiple time, so let's get rid of that. Include runs, everything is fine. Okay, failed runs.h file, it's missing. Runs.h file is missing. Why? Everything is fine. Okay, transport model, because of that. So fine, no worry. Okay, so we are set with a dependency. Okay, now we are set with the dependency. Okay, and so our model is ready to go. Before we go for further modification, let's check that either it is running correctly or not. For that, let's adopt the some standard test case. Okay, so for that, let's go to the our area tutorials, let's say incompressible, and inside of it let's search for the k omega file. That is the idea. So go to this area, okay, grep -r k omega. Okay, so we are using the in the mrf simple form simple mix. Okay, inside of it also we have a this entry here, or let me check for just omega. So with that we able to see the 0 folder. In whatever the 0 folder we have omega, we try to adapt from there. Okay, it's very simple. Okay, so simple form motorbike, that is one. Okay, and from that we able to adapt, or in simple form okay, it is srf. I want very simple test case, so we able to quickly run the case, or we can modify our existing test case as well. So let's do that way. Okay, so what the existing test case, so go to the test area. This is k epsilon. Okay, in case of this let's add up this and run for k omega as well. Okay, so let's say k my k omega. Okay, and when I say when my k omega, so what else we needed inside the simple form? If you let's say motorbike, okay, and here we require the omega file as well inside the 0 folder that is missing in the previous case. So let's open this and also open the omega file. So based on epsilon, the way we have this entry, okay, in the similar line let's have a entry for omega. Okay, so in epsilon, so I'm adapting very simple initializations. Okay, so in case of this, let's say something like some dummy value I'm keeping. Okay, and then what else we want? This is whatever we adapted, same value. Let's fix this. And in case of here, I go with the this as a internal field, and this one omega wall functions, and this is empty. So this is the simple way I adapted the file for omega. Okay, so we are set with the omega. Now go to the system folder. go to the constant folder, runs property. Okay, and here we have a k omega. In case of k omega, we say my k omega. Okay, and here we construct a new my k omega, so we definitely require the coefficient for my k omega SST model. Okay, so let's copy this and control paste. I say my k omega as a all the coefficients. So if you don't give, it's perfectly all right, then whatever is available inside the code, it will use it. Or if you want to tune the all the coefficient, then you give the value here and it will adapt accordingly. Okay, so I think we are set with this. So let me run the case and have an idea either what we did is correct or not. FE40 block mesh. Okay, so it's saying k omega model is not available. That is correct, because we have to add this line inside the control dict file. So go to the area, system folder, control dict file. At present, this is the file name we have. Okay, so along with that, you can add one new file name. Okay, so we are set with this file name. Let's see if we able to run the case. Correct. So what else we required? We required the Laplacian of this omega entry is missing inside the Laplacian scheme. That is correct, because the scheme and the solver we didn't adapted accordingly. So let's first go to the scheme. Okay, so inside the Laplacian we required this additional entry. Control V, save it. Then we require this divergence of phi omega entry in this divergence scheme here. So whatever we adapted for epsilon, similar entry. We try to add up this from this area, and whatever we have for epsilon, same thing we try to adapt here. Then omega is undefined inside the FE solution. That is correct. Okay, so inside the FE solution, like we have this in the similar line, let's have a omega value here. Okay, similar line, let's take pipe and omega as a residuals. Similar line, let's have a omega here. Okay, and cache for k omega epsilon, no worry. So I think we are set. It's running, but how we know that it is running? With the help of our new developed model. For that, let's write one line inside our main function. So where is the main? This is the correct is the main functions. So what we supposed to write over here? So for that, let's go to any of the application, solver, basic, Laplacian. Okay, and add up this one line. Okay, and try to write it down inside of it. So before it start calculation, we say calculating with my k omega SST. Okay, so with this entry, we know that whatever the model we develop, we are using that correct model or not. So sometimes this dependency resolution kill a lots of time. Okay, but be patient and try to look at very carefully and try to resolve it. Okay, so let's see. Yes, I am using with the calculating with the my k omega SST. So we are set with the template. So we develop the template and we now able to manage with our new developed model. okay. So but it is same, only we fetch the model outside. Okay, now let's try to understand this entire model and then we try to modify it. Okay, so when I say let's understand this model, so for that let's go to the area, and we have a very nice let's say all the equations that is available for k omega SST model. So inside the k omega SST, what normally happen is something like this way. We to quantify all the Reynolds stresses, we are using the Bossiness hypothesis. Okay, and for that Bossiness hypothesis, we correlate the Reynolds stresses with the help of the mean quantity in terms of the nu t. Okay, so for that we require the calculation of the nu t. So nu t we calculate based on the k and omega. So for that purpose we have a two equation, one for k, another for omega. So that is what we have this equation. Inside of this equation we have a transport rate of change of k, okay, and advection of k, then production term, diffusion, and the destruction term. Similar line, rate of change of omega, advection of omega, production of omega, diffusion of omega, destruction, and cross diffusion term. Okay, and f1 is F1 and F2. Okay, it will try to map k and omega and epsilon equation accordingly, and for that purpose we required this particular f1 f2. It is bending functions. Okay, and c dk omega, it is part of here. Okay, in the f1 f2. Okay, so this is this is different all the model parameters. So this all the parameter, if you see, okay, so you can see this all the model constant here. Okay, where you will see this all the model constant like alpha k1. Okay, so alpha k1, alpha k2, omega 1, omega 2, epsilon. Okay, and all this model constant based on whatever is implemented in OpenFOAM, it is also mentioned here. Alpha k1, alpha k. Okay, so alpha k1, alpha k2, alpha omega 1, alpha omega 2. Okay, alpha omega 1, alpha omega 2. Okay, all this entry. Then we require the gamma 1, gamma 2, then beta 1, beta 2. Okay, beta star, a1, b1, c1, f3. Okay, so this is all the required model constants. C1k is nothing but kappa. Okay, and from here beta star, b1, b2, gamma 1, gamma 2. Okay, kappa. Okay, so all these are c epsilon 1. Okay, c epsilon 1 somewhere maybe available. Okay, so this is all the required model constants. Okay, and let's say this is the set value, but if you want to tune this value, what you supposed to do? Go to the area where you are running. Inside that you have a runs. Let me open Guinea. Inside the runs, when you say k omega, so here we are writing the k omega SST coefficient. So you have leverage to choose whatever the constant you want to use. Okay, if you don't specify any constant here, then whatever is the by default inside of this, inside the code, it try to add up that constant. But if you want to tune that constant, you write it down whatever the constant you want to use. Okay, in the similar line, if you now see this area and this all the constant, you will know that more or like we are adapting something like this constant only. Okay, so couple of the things we can change, like c1 is nothing, c epsilon 1, a1 is maybe the change here as 0.31, alpha k1. Okay, then alpha k2, then omega 1, omega 2. Okay, then gamma 1, gamma 2 is from here, gamma 1, gamma 2. Okay, then beta 1, beta 2, and beta star. Okay, all these quantities here, and a1, a2, and c mu is also 0.09. Okay, somewhere it is mentioned, not mentioned, it is standard quantity in the turbulent. Okay, c mu is this. Okay, so this is how one can quickly try to check what model constant we are using. Now if you look at the equations wise, okay, so this is the release, this is the from the literature, this equation is coming. Okay, and all these values. Okay, So epsilon is nothing but beta star into k into omega. Okay, so beta star k into omega give you epsilon, and the model coefficient k epsilon and k omega model in the k omega model are calculated based on this f value. Okay, and f is nothing but this bending factors, and this f exactly give us the bending between the coefficient of alpha 1, alpha 2, beta 1, beta 2. Okay, and that is belong to epsilon and omega equation, and we bend both together and generate the k omega SST model calculations. Okay, so that is the how this is look. Alpha refer to corresponding to model constant. Now inside the OpenFOAM, this is exactly it is coded, okay, along with this limit, okay, for f1, f2 and all this. Now let's try to compare our source code, so it gives us exactly the idea. Okay, so let's say this is our this file, and let me open such a way that we able to see equation as well as our file. Okay, so this is, let's say, our equation, and let's say this is our code. So let me arrange the view. Okay, so this is our equations. So let's first look at the all these equations. Okay, so if you look at our C file, okay, so in the C file, each file we have to let's say declare all the required model coefficients. So we say dimensional scalar, and this is the switch f3. Okay, so between f1 and f2 we are switching, so that is the switch. Okay, wall distance, by default when we say wall dist equal to y, it try to give us the first cell height whatever needed. Then volume scalar field k, omega and nu t. Okay, then this is the volume scalar different f1, f2, f3 and f23 is the four functions we required. Okay, this is blending function between f1, okay, f1 and the psi1 and psi2. This is two constants, so we say f1 star psi1 minus psi2 plus this. It is nothing but exactly the same what is mentioned here, this one. Okay, so based on that we try to quantify the bending between these two constants. Okay, then we say alpha k, okay, bend between this one and this is its supply variables. Okay, so that is how one can check this. Okay, so if you rearrange this, what you get here, okay, so this and f you say separate out from here, so we have a f into of these quantities. Okay, like this f into psi1, whatever the you supply one variable psi1 minus psi2 plus of this one psi2. That is exactly we rearrange this equation in terms of this blending functions. And how we are blending, when say alpha k, we want to calculate the alpha k, we supply the f1 and alpha k1 and alpha k2. Okay, so what is alpha k1 and alpha k2? It is this model constant alpha k1, alpha k2, and it blend based on f1. What is f1? F1 is this function. So based on this function we try to blend this particular variables, particular alpha k, alpha omega, beta, okay, gamma, everything is blend based on that. This is the name with which we are able to access our turbulence model. Okay, this is the destructor and few member functions, like we want to calculate the nu t. Then this is the effective diffusivity of k, diffusivity of omega. Okay, so effective diffusivity of k and effective diffusivity of omega, what this term is here, whatever we get this diffusivity. Okay, so we have to quantify this diffusivity, effective diffusivity. We try to quantify, okay, based on alpha into nu t. Okay, so let me check again. So effective diffusivity of k, so that means this is laminar kinetic viscosity, this is turbulent viscosity into alpha k. Okay, so that is diffusivity this going to use. Same way omega diffusivity is something like this way, this is the diffusivity we are using. Okay, then k omega, epsilon wherever needed, then Reynolds stresses, that is R, okay, then laminar stresses, then this is the source term, okay, and corrector, okay. So this is the entire entry in the .h file. Now in the similar line, let's look at in the .c file. So first we have a certain functions we define like f1. So if you look at the f1 here, how is defined? F1 10h into bracket min max of this value, comma, out of this here also max of this y square, and like this way. So similar line, what we going to supply, we supply the CDK omega as a input with the f1 functions, CDK omega max, okay. So CDK omega, we define this, then we say argument 1 minimum of, so this is the argument entire 1, okay. So minimum of what we have, min, inside max we say scalar 1 divided by beta star, okay, this one, okay, then square of k, square root of k, this one, okay, divided by omega into y, same term, okay, then scalar of 500 nu y square omega, this term, okay, then so max of either of this, whatever is come, then minimum of this term and this 4 alpha omega 2 into k divided by max of CD k omega plus, and this max is appear here, max CD k omega or 1 10 to the power 10, same entry here, and into the that we have a y square, so and comma scalar 10, okay. So this gives us the argument 1, and we use the argument 1 as a f1 equal to 10h argument 1, okay. So if you see from here, you will get 10h of power of argument 1. Why? Because it's power of 4, okay. So this is f1. Same way f2 we say argument min max of scalar 2 divided by beta star square root of k omega y, 500, this all entry 100, argument 2. F3 we can quantify the 500 nu t omega scalar of this, okay, and 1 minus 10h power of 3, so that become f3. And then this f23 is if f23 of f2, and we switch between f23 and this f23 we utilize for the blending purpose, okay. And this is all the variables that we use, okay. Here we are creating the k omega nu t. We specify the bounding limit between for k and omega, okay. So k and omega supposed to be bounded within particular limit. Then nu t, how to quantify the nu t? So for that we have this formula, a1 into k, then we say max of, okay, a1 into k, max of a1 omega comma b2 f2, okay. So this is nothing but b1 f2 into square root of 2, this is the same thing, okay. It's written straight away like this way, symmetric tensor, okay. So and nu t correct boundary conditions, this is how we can quantify. Then all the volume stress field or Reynolds stresses we can quantify like this way, okay. And then we have a dv ref that is also we required for quantification. Now if this look boolean read option, read if present, that means if inside of this file if we have that coefficients, then only it's going to read, otherwise it's not going to read it, okay. So that is what it's going to read, otherwise it not read. Now correct, okay. So this is the main functions. Here we try to correct the our nu t, and for that we try to calculate the k and omega model equations. So here we first try to quantify the y plus value, then volume scalar field s2, okay, it is meg of this one, okay, s2, then we quantify the G is nothing but nu T into S2, update omega and G at a wall. Okay, then volume scalar fit CD K omega, this is what we calculate CD, this one, this value, okay, CD K omega, okay, that we try to quantify this value, okay, internal, this one, okay, that is what we have, gradient of omega divided by gradient of K, gradient of omega divided by omega into alpha omega 2 into 2, okay. Then we, based on that, we quantify the this one, okay. Now this is the omega equation, so let's look at the omega equation, how look like. So we have a this term, second term, okay, source FVC divergence phi of omega, okay. So it is ultimately we try to segregate this for stabilizing the equations. Then Laplacian term, okay, that is coming from this side, okay. So for that we require the effective omega, okay, this one into F1 we specify and we get this. Then gamma of F1, gamma into F1, okay. Then we have a this source term as well along with that, okay. So gamma F1 FVM of SUP, so that is coming from cross diffusion part, okay. So this is all the terms, beta square into omega, this term, okay. And this is the F1 minus scalar of 1, okay, source term, and CD omega divided by omega into omega. So we try to, it is nothing but almost like a CD omega term only, so we already quantify the omega, from that we are generating that term, that's it, okay. So this is how we able to look at the omega equation. Then this is the K equation in the similar line, so this is exactly what we have. Then we say nu T is equal to what we say, A1K max of this, and we quantify the nu T, okay. And then we say correct the nu T and minimum of either this or nu T ratio divided by nu, okay. So either of this we can fix this nu T, and this nu T allow us to quantify the Reynolds stresses inside the our Navier-Stokes equation. So this is how entire our equation is coded if you compare the existing model and the this whatever the equation we have, okay. So this is the few mapping we have, okay. Now if we want to modify, let's say, this particular model, so what modification we are expecting, let's try to quantify that as well, okay. So let's try to modify these equations based on our requirement. Now let's try to modify our SST template, okay. So in this paper they propose very nice scale adaptive filtering aspect, okay. So this is very nice paper, and we try to adapt that filtering aspect in. So if I summarize, upper limit of the modeling length scale is applied to the nu T, okay. So some of the upper limit, like this way, we try to restrict the filtering aspect, okay, and based on that we try to quantify the this nu T. For that we have a length scale LT, okay, and here they quantify the LT based on different things, okay. So LT is they mention here nu T, and the LT is nothing but K square by omega, okay. And then we try to restrict the nu delta F, that is the largest length scale, okay, in terms of some quantity, okay. And based on that, at the end we try to quantify the this nu T, okay, near wall assumption, all this thing. So we try to add up this particular concept inside the SST model, so that is the idea. So ultimately we want to code this few lines inside our existing SST template. So I already constructed the solver, okay. So I gave that name as a K omega SST FES scale adaptive functions. Okay, so let me quickly give you the idea how exactly the code look like. So if you look at no need to change anything in the .h file, only the change appear in the .c file. So inside the .c file, okay, one change appear in the .h file, so that is the name. I gave the k omega SST SAF model. Okay, and along with that, if you look at the this C file, okay, we need not to change anything, but what change we required at here, in previous case we are calculating the nu t based on this our standard functions, but in case of this, now we want to calculate the nu t based on this new functions. So for that we require LT and all this calculation, and LT is coming from this particular paper, k square over omega. Okay, so depending on that we try to quantify the and along with that we quantify the one constant as a alpha here for this filtering length scale, limiting length scale. We required alpha, and alpha equal to 3. We try to quantify any value more than 1 is acceptable, so we fix the 3 that exactly given in the paper. So we say alpha equal to 3, then alpha is a scalar field. This is one scalar number, it not scalar field, it's just scalar. So we say, and but LT and small lt are the scalar field, so we quantify this LT and this LT. Okay, so both the things we try to quantify, and this LT is nothing but this our filter delta, this one. Okay, so that is what we try to quantify. So square root of k divided by omega, but here we always have to multiply by beta star in case of k omega SST model. So we multiply this with the omega, so then we get exactly the length scale LT, and from the LT we try to code this particular function alpha into max of this or this delta, and delta is coming from the mesh. Okay, so exactly that is what we try to figure it out here. Okay, so same way we say alpha. Okay, so let me fix it here. So we say alpha into form max. Okay, so that is form max we want. Then we say form power of this quantity 1/3 mesh and volume field. Okay, so with this it give you the volume of that each cell. Okay, that is this quantity, and max of either this or this. So here we can say the magnitude of velocity and the at that time what is the delta t. So that is what we quantify, and we kept as an internal field. So with that we quantify the LT as a scalar field. Okay, so like that way we quantify this LT. Then nu t corrections, so something like this way we can quantify the nu t corrections. So mean of LT by LT. Okay, so and then we say and of that we say power of this one 4/3. Okay, and so we slightly modify based on our requirement. Then we say alpha k max of alpha 2s2, and so this is nu t we modified, and then we say it is internal field. So this is how one can quickly add up the new SST model as well. Okay, and then we try to compile it. Okay, so let's go to the area and try to compile the test case. So let's go there, wclean.all, and say wmac libso. So we compile it. Okay, so one time you know the template creation and resolution of dependency, it is not difficult to develop a new solvers, or develop a new library as a new turbulence model. Okay, so that is exactly what we are doing here. Okay, so we are set. We gave the name as a k omega SST. Okay, and SAF turbulent model. Okay, so that is the library name. Now when we want to run it, we supposed to fix that library name inside the control dict file. Okay, so inside the control dict file I fix that name, and along with that we supposed to change the name inside the our constant folder runs property. Okay, also we say now SAF SF model. When we say SF model here, make sure we have SF model constant as well. Okay, now let's run the case. So it is running with SAF, but look, it is a dummy case. Okay, so you will observe its divergence or anything because we didn't set the case properly. Okay, so even though you run with the simple k omega model, because we adapted this case from the k epsilon based model and simply we change the name as a k omega. Okay, so you may observe the divergence, but it not mean that our coding is failing. It means that our setting is not appropriate. Okay, so if you set the test case appropriately, you will see the convergence as well. Okay, but here our idea is that to quantify either our model is we are selecting the same model or not, and we able to manage the template creation and the new turbulence model creation, all these things. Okay, so I didn't went inside of this particular test case and quantify what's wrong, so that's why it's diverging. Okay, but you can adapt other tutorial, like from let's say from the form area. Let's say if you go cd form okay, form extended tutorials. Okay, and let's say grep minus r omega. Okay, and find out what different test cases has this omega. So if you look at here, in here also you will get a this entry, or you can type k omega, k omega, and say SST search, where we are using this k omega SST model. So incompressible motorbike test case we are using, so you can run our new developed model on this incompressible simple bike model. Okay, and figure it out either we are getting the converged solution or not. Okay, so couple of tutorial is available inside the release version, so you can adapt that. Okay, and straight away try to compile. So what we learned in this particular session, try to adapt the particular models from the let's say src folder, fetch that model out, resolve the dependency, compile it, and create the template. Now one time the template is ready, then you have to code based on your requirement of new turbulence model. Okay, so that is what simple thing we learned in this particular session.